And if it does follow, then we understand the physics and we can solve it. And even if it doesn't, we may not understand the physics, but we may be able to solve it. And second level, we use the exact so to solve it, we use the existing solution of Fick's second law, which really is about how the concentration gradient affects the speed at which they diffuse or spread. So for example, for like ink, and drop of ink in the water, because of the higher concentration of the ink, it eventually spreads and make an equilibrium where the concentration of the ink is just even throughout the water. However, the speed at which occurs, it probably happens a lot quicker at the beginning when the concentration is really higher, and then it slowly, the speed at which they diffuse kind of slows down, right? So it kind of combines the concentration gradient and the speed at which they diffuse. So we have these two concepts, the MT, which is the mass change as a function of time, and then this M infinity is a net mass change at equilibrium. So for the steady state change, at the steady state, how much mass has changed, and we can define by the M sample at T is equal to infinity minus M sample when T is equal to 0. So for example, if you have this where the mass of the hydrogel is like 1.1 gram and the humidity is like 10%, and time is equal to 0, we set the humidity to equal to 80%, and then like 3,000 minutes later we see that the mass has increased to 1.6 gram. So in this case, the M infinity would be a 0.5 gram because 1.6 minus 1.1. But if there's another case where the T is equal to, for example, like 300, and then this is equal to let's say 1.4, then in 1.4 gram, and in this case, the MT at T is equal to 300 would be 0.3 gram, right? And so we often use MT over M infinity, and when the T is equal to infinity, then this would be 1, and at 300, for example, this would be 0.3 gram over 0.5 gram, right? So that would be like 60% or 0.6, and that kind of tracks the progress of the reaction. So we have this Fick fingerprint. So this ratio MT over M infinity is linear in square root over T for short time, which is defined by this is slower than 0.5, because it makes sense because it tracks the progress of the reaction. So the reaction progression is less than 50%, so we call it a short time. And in the other hand, when it's higher than 0.5, we call it a long time. And in that case, it's ln 1 minus mt over m infinity is linear in T. So imagine if you have this spherical hydrogel where the diameter is, there's one of them is diameter is 1 millimeter and another is diameter is 2 millimeter. In that case, we can expect that the one with the smaller diameter will reach the steady state or equilibrium faster because of the higher surface to volume ratio, right? But one can ask by how much, right? And in that case, it would be by 4 times. That's because of the diffusivity. Diffusivity in 3-dimensional, we can define by 1/6 frequency times the characteristic length times or squared. And because the characteristic length, the diameter, is differ by 2, and so it's gonna and diffusivity will differ by 4, so that's how much it will differ. And imagine this scenario where, so this is just really just saying the higher the concentration, the diffusivity, higher the diffusivity. So imagine like a hydrogel in the water or you know, humid air. Higher the concentration of the water, higher the diffusivity. So you can imagine if the higher the humidity, hydrogen will absorb the water faster, right? So that's what we're really saying. And so this is a loading phase, and then so we may stare at the mirror somewhere around here on concentration, and the concentration will accumulate as the time goes on. The hydrogel will absorb more water and more water, and the diffusion or diffusivity increases, which means the rate increases. So it goes faster and faster, and until it reaches steady state. So that's the loading. Well, what about the unloading? So let's say hydrogel is drying, right? First of all, there's a high concentration of water within it, so the diffusivity is pretty high. So it also dries pretty quick. But as you get drier and drier and the concentration decreases, diffusivity decreases, and then so does our unloading. So that's why they do not share the same path. In this case, this is the opposite. So we can imagine like a hydrophobic material in the water, right? So as there is a higher concentration of water, the water tries to just bind to itself rather than going into the hydrophobic material. So that's why as the concentration increases, the diffusivity decreases, and we see that with the opposite result. So as we load and load, the diffusivity decreases, so it slows down. But when it's unloading, so as the water evaporates and there's less water, so the water has less friends to interact with, so it's forced to interact with hydrophobic material, and then it just slows down faster. That's why the unloading is faster than the loading. And sometimes to solve problems, we use the constant diffusion coefficient cases, which utilizes Fick's second law as usual. And there's a thing called Bessel function of the first kind, which is solution is this, which is solved by Bernoulli, and this shows just when n is equal to this, n is equal to 0, and this is n equal to 1, and it goes and so forth. And this 0, this point when which is x is equal to 0, the value of j when the x is equal to value of x when j is equal to 0 is called a root. And once we know that, we can utilize this Bessel function table to solve problems. But how does it come into play? Well, so we have these tables that utilize, there are a lot of different diffusion scenario. For example, this is infinite cylinder with a certain radius, and there's a concentration given, and we want to find out how to mt over m8 m infinity. So which represent the progress of the reaction. And this when this j actually not this one, or this is really similar, but here we are solving for concentration, and we have this j terms coming in, but what it actually represent, I'll cover in the next video or put in the description for the explanation.